Welcome to the Biochemistry Clinic, and today we are looking at beta oxidation. And I hope you've seen the video on activation of free fatty acids as well as the carnitine shuttle, because today we are simply focusing on what is happening in the matrix of the mitochondria after the activated fatty acid CoA has been shuttled into the matrix of the mitochondria. And this is beta oxidation of saturated fatty acids. Now, there are basically 4 steps that I want us to consider. The first one is dehydrogenation of the fatty acid CoA. Now, what is happening here is that you are actually removing 2 hydrogen atoms. And these 2 hydrogen atoms that are removed from the fatty acid CoA will be accepted by FAD to form FADH2. And that's why you are producing FADH2, because FADA is actually accepting the 2 hydrogen atoms that are part of the fatty acid CoA. And when you do this, you actually create a double bond between carbon 2 and carbon 3. Again, we're going to see the significance of this double bond. And remember, this double bond which is formed is in trans form. That's why the product is known as trans-enoy-CoA. The enzyme responsible for this step is acetyl-CoA dehydrogenase. In the second step, you have hydration, or simply the addition of water to your product here, which is trans-enoy-CoA. Now, what happens when you add water to trans-enoy-CoA? You are going to form beta-hydroxyacetyl-CoA, and the enzyme for this reaction is known as enoy-CoA hydratase. Now, this enzyme is very critical. Again, we're going to appreciate its importance when you look at the beta oxidation of unsaturated fatty acids. In step 3, we have another dehydrogenation reaction. This time around, the beta-hydroxyacetyl-CoA is being dehydrogenated, and then a beta-keto-acetyl-CoA is formed. The enzyme that is responsible for this is beta-hydroxyacetyl-CoA dehydrogenase. And remember, since this is a dehydrogenation, again, we are removing 2 hydrogen atoms, one of which will be accepted by NAD+, which is going to form NADH, another very important electron carrier, plus a hydrogen is actually also given out in this step. And finally, in step 4, we're going to have cleavage of the beta-keto-acetyl-CoA, which is actually produced in step 3. So this cleavage leads to the formation of acetyl-CoA and a new acetyl-CoA. Now, this new acetyl-CoA is 2 carbon atoms less than the one that we started with. So in this instance, we are using palmitate as an example, which is a 16-carbon fatty acid. So it means that after step 4, you are going to give out acetyl-CoA and remain with a 14-carbon fatty acetyl-CoA, which will go back into this oxidative cycle until all the carbon atoms have been cleaved, 2 carbon atoms at a time. And the enzyme in step 4 is known as thiolase. Now, in terms of energy production, how much energy is produced in terms of ATP from palmitate, for instance? If we completely oxidize 1 molecule of palmitate, palmitate is a 16-carbon fatty acid. So it means that for you to completely oxidize this means chopping 2 carbons at a time, 2 carbon atoms at a time. You are going to need to do this 7 times, or you need 7 rounds of beta oxidation to completely oxidize a 16-carbon saturated fatty acid like palmitate. Now, for each of those 7 rounds, you produce 1 FADH2. So 7 times 1.5, you get an equivalent of 10.5 ATP. The same applies for NADH. After 7 rounds of beta oxidation, you produce 7 NADH, and we know that each NADH molecule is equivalent to 2.5 ATP. So 7 times 2.5 should give us 17.5 ATP. And at the end of this beta oxidation, you are going to give out 8 acetyl-CoA molecules, which can produce an equivalent of 10 ATP molecules each in the TCA cycle. So 10 times 8 to give us 80 ATP molecules. So meaning that the total yield is 10.5 plus 17.5 plus 80, which gives us 108 ATP molecules. Now, remember the activation process of free fatty acids. We used 2 ATP molecules in that process. So we're going to subtract the 2 ATP molecules that we used in the activation of free fatty acids to form a fatty acid-CoA. And once we subtract that, we're going to get a net yield of 106 ATP molecules just from one molecule of palmitate.